pitch though, for only the first time student.
Yeah, but that's a lot, 100
That's
students.
what I was thinking, not that many people are probably gonna go.
I'm like, yeah, well, it could be you. So like, did you guys do like the whole Taco Bell Cinco de Mayo thing? We went through
No.
drive-through.
I forgot about that.
I'm like, so yeah, my daughter was like, let's go, Mom. So before she went to school, she got her free $5 breakfast thing. Taco Bell.
I heard about it, but it just kind of still weirds me out to have breakfast there. I don't know.
Just something not right about it.
Yeah.
Okay. So we're building up to actually batteries, believe it or not, like the chemical cell batteries that you use in your calculators and stuff. But we need to talk about oxidation reduction reactions. In order to do that, we need to assign oxidation numbers. And so actually we did this in class. Gosh, this is Monday. We did this in class. We said that you can actually, I'm going to come up with an alternate way to do this. You're going to be, well, why'd you show me this? Well, because. But you can, and it's something similar to what we did in Chem 1, but that was formal charge, and this is actually the oxidation number. What you need to know is that chlorine is more electronegative than carbon. Oxygen is more electronegative than carbon. And so because of that, the two electrons that are actually part of that chemical bond, they go with the more electronegative one. Okay? And remember then, that number is right here. Okay? So the number of electrons at the ionic limit. This first number right here was just, it's from the periodic table, it's group number. And so you do a subtraction to get the oxidation number. So we said the oxidation number for carbon, and somebody said, do you always, like, would you do a +4 or just 4? No, you say +4. That's what I do anyway. We said that carbon is a +4, each of the chlorines are -1, and oxygen is a -2. And somebody pointed out, well, dude, that whole thing, if you sum those together, you get 0, and that's true. Okay, so that is finding the oxidation numbers for each atom in that particular compound. Well, there's an easier way for coming up with oxidation numbers. So these rules we're going to talk about are actually what we're going to use today in lecture and tomorrow in lab too. So first off, if you see anything that is in its uncombined elemental form, okay, so for instance, if it was FeS, like iron, okay, its oxidation number is 0. If it's H2, gas, its oxidation number is 0. Okay, notice how H2 is in its uncombined with anything else elemental form. Okay, you kind of get the idea. If it's aluminum solid, its oxidation number is 0. So that's kind of fun. So that's one of many rules. Here's another rule. If you have something that is a monoatomic ion, and we spent some time in Chem 1 talking, for instance, that sodium forms a +1 charge. Okay, actually, its oxidation number is +1. We said that things in 6A, like oxygen, form a -2 charge. Okay, actually, its oxidation number is -2. Or -2, I guess I should say. That's how that kind of works. So that's kind of nice. Here's one. The oxidation number of an atom in a polyatomic ion composed of only one element is equal to the charge on that ion divided by the number of atoms in the formula. The two examples we're going to look at here in a minute. Everybody's favorite, Hg2, 2+, the mercury 1 polyatomic cation. Remember that? Doesn't that not drive you nuts? Okay, so what this says is basically you take the charge. Oh, first off, let me remind you what that looks like. Hg, covalent bond, Hg. All running around with a +2 charge. That's the mercury 1 polyatomic cation. So what you do is you take +2 and you divide it by 2, so each one of those is a +1. That's it. There aren't very many examples of polyatomic ions composed of only one element. Okay, the other one we're going to look at is I3 with a -1 charge. All right, another rule. Now these are very helpful, okay? This has to do with hydrogen. So anytime you see hydrogen, for most purposes, anytime you see hydrogen, think it's going to be +1. So here we go. H2O, okay? We're going to need to assign oxidation numbers for those two hydrogens and that oxygen. Each hydrogen is going to be a +1. That's it. Unless hydrogen is combined with a metal, okay, which we aren't going to deal as much with those. So hydrogen +1. Number 5. Again, I bring back the water. The water molecule, okay, we need to be able to come up with an oxidation number for those two hydrogens. I told you for the previous rule, it's going to be a +1 for each of them, for each. That oxygen's going to be a -2. Usually, almost always, oxygen -2. But here's one for you. What if it was O2, gas? Then it goes back to being oxidation number of 0. Okay. And here's one for you. Actually, we ran into this with the example we started out with. When you finish assigning oxidation numbers for everything in a neutral molecule, it needs to add up to be equal to 0. That's what we looked at. You guys kind of picked that up in Wednesday's, or this is Wednesday, in Monday's example. So actually, this rule number 6 can help you deduce things that you need to deduce. Okay, you can hang your hat on oxygen being -2, hydrogen being +1, but if you have to deduce, we'll show you some examples how you can kind of backtrack. So what if you're dealing with something that's not neutral but something that has a charge? Well, then the oxidation numbers need to add up to that charge. Okay, and we'll look at some examples of that. So looking at some examples here, H2, oxidation number 0. Actually, each hydrogen atom in that molecule is oxidation number 0. How about magnesium? Magnesium solid. Also 0, yep. What about phosphorus solid? 0. Uncombined elemental form, 0. What about the sodium that's a +1 cation? +1. Yep. That's it. All right. The nitride ion, -3. Oxidation number -3. We already talked about these, the mercury 1 polyatomic cation, Hg2, 2+. They're each one a +1. Okay? Now, I didn't say that oxidation numbers have to be integers, did I? So here we go. These are not integers. This is the iodide polyatomic ion, where we have 3 I's combined to have an overall -1 charge. -1 divided by 3 is -1/3. So actually, that's the oxidation number of that. So now we get to some things where, well, if you're given a formula of anything, whether it's a molecule, a formula unit, or polyatomic ion, you can and you will want to be able to look at each atom in that formula and come up with an oxidation number. We already did water, because 2 of the rules we talked about, one was for hydrogen is a +1, and another rule for oxygen is a -2. But can you already see where if you take 2 times +1, you get +2, plus -2, I mean, it adds up to 0. So it's going to be my point there. So now we get into something that's a little bit different. Okay, my convention is to go this way. I'm going to put a -2 over the oxygen because I just know each of those 4 oxygens are -2. I'm going to put a +1 over the hydrogen. Each of those hydrogens are +1. And then sometimes I'll do this mathematically, sometimes I'll just do it in my head. Let's try it mathematically. So do you see where we have 2 times +1 plus 4, because there's 4 oxygens, 4 times -2. Okay, let's see. Let's just go ahead and see what that's equal to. So I got a 2 minus 8, that is equal to minus 6. Does that make sense? Okay. So for this whole thing to be neutral, do you see where we have just deduced that this must be a plus 6? We have figured that out. How did we figure it out? Kind of going the outside, working our way in. That's exactly how that works. Okay. So let's do a similar thing for ammonium cation. I'm going to go ahead and red is going to be the one I can hang my hat on. I have a +1 for each of those 4 hydrogens. So I have a +4 collectively brought here. So do you see where if I make this a -3, -3 plus 4 is equal to +1? That is actually the answer there. Okay. Nitrogen's not always -3 oxidation number, but it is there. And we got to deduce the last one too. Again, oxygen, I'm going to put a -2 on the top of it. -2, there are 2 of them. They collectively bring a -4. If I make this a +3, do you see where it's overall -1? So +3 is the oxidation number, oxidation state, oxidation number, both of that chlorine atom. How did we know that? We started with the oxygen, which we can hang our hats on. So at the crux of your chemical cells is understanding oxidation numbers. Okay, so when something, we're gonna switch gears from just species, from molecules and compounds, to basically chemical reactions. So we're going to, with chemical reaction, have a reaction arrow here, okay? So basically, oxidation means that you have gone from, I'll put the letter A as an element. You have actually increased oxidation number. An example of an oxidation would be if something goes from 0 to +1. Okay, A is being oxidized. Oxidation, increase in oxidation number. Another example is if something goes from, I'll just switch colors here, from like a -3 to a 0. Okay, you see where that's oxidation? So oxidation is basically that same atom on either side of the reaction arrow is increasing its oxidation number. Reduction is the opposite of that. So if I look at reduction, I'm going to go ahead and draw I'll pick on B. I don't know if I need to necessarily, but I'll pick on some atom B. Okay. On either side of the reaction arrow or chemical equilibrium arrow, the oxidation number has decreased. So, for instance, it could go from a +1 to a -2. That would be reduction. We'd say that B is being reduced. Reduction is occurring. Picking another example, we could go from -2 to something more negative, -4. Reduction is occurring. So I've been talking, kind of building up to, and we'll talk more about this maybe Thursday, but for sure Friday, your batteries, your electrochemical cells. Your electrochemical cells work kind of like your electrical outlet from the wall. Basically, electrons are flowing through there and they're getting work done. Oxidation, when it's going from a lower number to a higher oxidation number, can be viewed as losing electrons, and reduction can be viewed as gaining electrons. And this kind of makes sense to me because if you lose electrons, you're going to become more positive. That's oxidation. If you gain electrons from left to right, you pick up electrons, you're going to become more negative. So actually that whole thing works pretty good. So the examples we've already looked at, we basically take a molecule or it could be a pure substance, Pure substance as in is uncombined elemental form, but we put an oxidation number over that thing, and we can look at the other side of the reaction arrow and see if that oxidation number is increasing, okay? If an oxidation number for a particular element is increasing, whatever thing that element in, okay, is called the reactant that's undergoing oxidation. Now, is the whole thing undergoing oxidation? Not necessarily, just that element, just that atom of that element. Okay, but we say the whole reactant is undergoing oxidation. Similarly, when we look on either side of the reaction arrow and we identify that something is being reduced, its oxidation number is decreasing, okay, we say that entire reactant is being reduced. Okay, the reactant is undergoing reduction. Even though it's just one, and you know what's possible, quite possible, I don't know if I have any examples for you, I bet I do, that actually the same substance has the two atoms that are undergoing oxidation and reduction in the same substance. So that's always kind of fun. A little bit of semantics, and sometimes I don't know why we really have to introduce this, other than you've probably heard of safety-wise, we need to know in our chemistry storeroom, for instance, what are our strong oxidizers. We need to know who those are, what they are, so we can store them together. So if something is an oxidizing agent, honestly, that is the thing that's going to be reduced. So an oxidizing agent means like an oxidizing reactant. And it's the reactant that's going to be reduced. Okay? I have that down here in blue. So the oxidizing agent is the agent that has the thing, the atom, okay, that is going to be reduced. Oxidizing agent is the thing that's reduced. Then I have a pair here that go together. The reducing agent is the thing that's ultimately oxidized. The reducing agent is causing reduction to occur at the expense of itself, basically, and it's becoming oxidized. So reducing agent is the reactant that's being oxidized, and oxidizing agent is the reactant that's being reduced. All right. So we've talked about combustion reactions before, but in general, combustion reaction is when you look on the product side, most things have oxygen in them. That's a combustion reaction. Okay, we've most dealt with, if you burn something like a hydrocarbon, if you burn hydrocarbon, add oxygen, you end up with carbon dioxide and water, which both have oxygen in them. So combustion reactions, I'm going to prove to you that a combustion reaction, actually, if you look on either side of the reaction area, you'll see an atom that's being oxidized and an atom that's being reduced. And these worked in my office, so we'll see if they work here. So, of course, those stoichiometric coefficients don't really matter, right? It's looking like a 0 for the iron, a 0 for the O2. And then over here on the product side, remember I told you that we're going to go with -2 is the oxidation number for that oxygen. Let's see, so -2 times 3, so that's -6 collectively. So it's looking to me like this is a +3. Okay, that's kind of how that goes. So I could go ahead and draw kind of like these little arrows. So I could connect the iron. I could say iron's going from a 0 to a +3. And actually, to me, I'm going to put oxidation. Okay, because it's going from a 0 to a +3. Well, then the other thing better be reduction. Let's see. Oxygen going from a 0 oxidation number to a -2 oxidation number. Yep, thank goodness. For one of your homeworks, you need to identify what's wrong with the chemical reactions that are in your textbook. And if it's supposed to be a redox reaction and you can't find oxidation or reduction, then something's not quite right. So, of course, the atom that's undergoing oxidation, that would be Fe. This is all going to go away, by the way. Okay. The Fe is going from 0 to +3. Which atom is decreasing its oxidation number? That would be the oxygen atom, going from 0 to -2. Still with this same reaction. What is the reactant being oxidized? Well, the reactant being oxidized is the thing that is holding the atom that's being oxidized, which it would just still be the Fe, S. Okay? Which reactant is being reduced? That would be the O2. So which reactant is the oxidizing agent? That's the reactant that's being reduced. So that would also be the O2. The reactants that is the reducing agent would be the thing that's being oxidized. That would be the FeS. So that's how you answer that. Not bad. So we're going to take a look, I think, at this one. But this is pretty cool. You guys did you guys do it? I think you did. Maybe not. But this is copper 2 sulfate. That's the blue stuff. Okay. The silver stick is actually solid zinc. Okay. And notice what can happen with this redox reaction. The zinc will go away. It'll become zinc plus. Well, it won't go away, but from solid to its in aqueous solution. And the copper will go from being copper +2 to a copper solid. So it looks like this. Okay, that is the chemical reaction between zinc and copper 2 sulfate. Just for kicks, and I think we got time, let's kind of put some oxidation numbers on top of those things down there. So the zinc I got at 0. Let me know if you have any questions here. Now the copper 2 sulfate, this is where you're going to have to, I'm counting on you, or you're going to need you to use your Chem 1 skills to recognize that actually that's copper +2, because you know sulfate is collectively a -1. Okay? That is a +2. The oxygen, we can hang our hat, and that's a -2. So let's see, sulfur there. Let's see. I almost said 0. No, it's not. Okay, so we have 4 oxygens. They're each a -2, so that's -8. +2, that knocks it down to -6. So I got +6 for that one. See how that works? And let's go on, continue on. Zinc, we know, is always a +1. Okay. And the sulfate here, yep, it's going to still keep its -2, and that's still going to be a +6. We could convince ourselves, but I just recognize since it's still sulfate on both sides, it's going to have the same oxidation number. The copper is, I got 0. Hang your hat on that, right? So if we were to identify the two things, these are kind of fun actually. You can see the zinc going from 0 to +1. Looks like it's being oxidized. Okay. And you can see the oxygen, you can see the copper going from +2 to 0. Looks like it's being reduced.
Shouldn't zinc be +2?
Oh, you're right. It doesn't change it, but you're right. Let me find my little eraser. Thank you. Because I look over it, there's like zinc and cadmium are both +2. Yep, silver's +1. The bane of my existence. Okay. Very good. So, I guess I don't need to do these again. Are we okay with kind of what we came up with? So the reactant, not the atom, but the whole reactant that's being oxidized would be the zinc, because it's going from 0 to +2, right? The zinc solid. The reactant that's being reduced, not just the atom, but the thing containing it. And actually, I think I'm going to go with just simply the copper +2 cation, okay, because it's an aqueous solution. So the copper +2 is the thing that is going from +2 to 0. The oxidizing agent is the thing being reduced. So actually that would also be the copper +2 cation. The reducing agent is the thing being oxidized. So that would be the zinc solid. So it's kind of like that. So here's a first look at those little electrons being transferred in a redox reaction within electrochemical cell. And add them together, this is what you get. So again, this is what we're going to be doing in lab tomorrow. Let's take a look at this one right quick, since they're so fun to do. I'm going to put a 0 over the zinc here. For the MnO2, I'm going to put a -2 for the oxygen. So let's see, -2 times 2, that's -4. So we can deduce then that the manganese there is a +4. I have to make sure I said manganese, not magnesium. Manganese is a +4. Going on the product side, go ahead and put our -2 for the oxygen, a +2 for the zinc. And for the Mn2O3, we'll put a -2 for that oxygen also. So 3 times -2, that's -6. So that manganese needs to be a +3. So if we look at both sides, let's see if we can find something being oxidized and something being reduced. Looks like we're okay. I see zinc going from a 0 to a +2 state. And I see manganese going from a +4 to a -3 state. So that manganese is reduced. Okay, and the zinc is oxidized. There's just a bunch of pictures now. Okay. Let's just pick one of these. I'm getting kind of restless with all these videos. Let's do the second one. Put up here, just for kicks, kind of from left to right, looks like zinc is a 0 oxidation state. Hydrogen and HCl is a +1. That makes that chloride ion a -1. We can deduce that. Zinc is always a +2. Okay, so chlorine there is also a -1. Hydrogen gas there is a 0. Each of those are 0. So let's kind of look for our pairs. Looks like zinc is going from, again, a 0 oxidation state to a +2, so it's being oxidized. And hydrogen is going from a +1 to a 0, so it's being reduced. If we look at the bottom one down there, copper, we know since it's uncombined elemental form, that is 0. The oxidation oxidation state for a +1 silver cation is +1. Copper +2 is +2. These are pretty easy. Silver solid would be 0. So we can, again, kind of match them up. The copper looks like it's being oxidized, and the silver looks like it's being reduced. All right, let's skip that video, if you're okay with that. You want to see the video? No, okay. So, but let's go ahead and just check out what we got. Looks like we have a 0 oxidation state and a 0 oxidation state. You're like, really? So if you look on the product side, again, back in Chem 1, hopefully you can recognize that's an ionic compound. Aluminum is a 3A metal, so it forms a +3 charge. And those bromine atoms are -1 because they're group 7A. They pick up 1 electron. So matching up stuff, looks like our aluminum is being oxidized. And our bromine is being reduced. So let's take a look at these. These are almost your last problems that are going to be due. I think they might be. I just hate to get you excited and there's more problems due. Okay, these should be it. So actually, I've done the first one for you. Okay. So that leaves B, C, and D for you guys to do. Oh, maybe, yeah, I did. And it looks like this. So basically, just go along and combine oxidation numbers for everything. And then you look to see if anything's being, or a pair of things, something's being oxidized and something's being reduced. And here my note to self, or my note to you guys is, I could not find anything that was changing its oxidation state or oxidation number. So magnesium was a +2 in both cases, carbon was a +4, oxygen a -2, hydrogen a +1. So if you were trying to look for a redox reaction, this one is not. Okay, so that leaves B, C, and D for y'all. The next one looks like this. Explain why they can't occur as written. And again, once you assign the oxidation numbers for everything, you'll see that iron is going from a +3 to a +2. Okay, so it's being reduced. And in this case, manganese is going from a +7 to a +2. It's also being reduced. So you should be scratching your head and you're like, electrons need to come and go, and it's not happening. So that left B for you. So in other words, you only have to do 34B. And then the last one looks like this. What are the oxidizing and reducing agents? So I remind you that agents, okay, so for instance, the oxidizing agent has the thing that's being reduced. The reducing agent has the thing that's being oxidized. And then I think I went ahead and did A for you, just because I find them so much fun. So just put the little oxidation numbers under everything, and you'll find that the sulfur is being oxidized. So it must be whatever contains a sulfur atom is the reducing agent. All right, are we good with that? I thought so. Okay, now we are going to go ahead and still take 10 minutes and see how far.
Are we going to skip that last slide?
Oh, thank you. Last slide really kind of leads us into the what lab is tomorrow. So tomorrow's topic is, and a little bit today, balancing a chemical equation using, not by inspection. So, we're used to doing inspection and making the coefficients match up. Well, in this case, we're going to use what's called the balancing by half equation method. I'm not sure, but they have to be redox reactions in order for this to work. This alternate way of balancing them. They are usually the spectators are removed, net ionic form. Ultimately, when you balance them on either side of the reaction arrow, it needs to be balanced both for mass, which we're used to, and charge, which we may not be as much used to. And in balancing them for charge, you're actually going to see the electrons kind of coming and going. Basically, the electrons that are given up by oxidation will all need to be consumed by the reduction half. Okay. All right. Yeah, I guess we'll go ahead and stop because it seems like 10 minutes isn't far enough to get through the first example. Because what we do today, we'd have to do again probably tomorrow. So, but I know some of our labs have been